Okay, students. So I'm going to do this activity to understand what static electricity is. You are familiar with this concept. You all know that insulator materials, because of charges on the surface of these insulator materials, they can attract very light particles like regiform pieces, tiny pieces of regiform, tiny pieces of paper, or even dust. So here I have some insulator materials. You are familiar with this: a plastic comb, the plastic tube of a pen, a straw, then the ebonite rod here, and the PVC pipe. These are all insulator materials. And to get the static electric charge on the surface of these materials, we need to rub them with another material. When you rub a comb either on your hair or on a piece of cloth or piece of polythene sheet, then the static charges will be generated. So to rub these materials, I have a piece of polythene sheet, a piece of wool, and a piece of cotton cloth. So we will try this activity and see how these charges attract these particles. So if I take this comb, if I hold it near these regiform balls or the tiny pieces of paper, it does not get attracted. Now you can either rub it with on your hair, the hair should be dry, not oily, or else we can rub it with a piece of polythene sheet. So when I rub it, we have to rub it nicely, and if you hold it near pieces of regiform, here you can see the pieces getting attracted there. So that is due to the charges generated on the surface of the insulator. That is the static charge. Now same thing we can try with pieces of paper. If I hold it here, now you can see the pieces getting attracted to it. Can you all see the pieces attracted? So that is again due to the static charges. Now how do these charge occur? The static charge generated. Comb is made up of atoms. It has electrons, negative charges. Now when I rub it with a sheet of polythene, negatively charged electrons flow from one material to the other. Because of that, there are charges generated on the surface of this comb. And those charges do not move. Because of that, we call them as static electric charges, and those are the charges that attract these substances. Now we can try the same thing with a tube of a pen. That also can be used to do the same activity. Now if I hold it near regiform balls or pieces of paper, there is no attraction there. But if I rub it with polythene, now if I hold it near pieces of regiform, you can see they get attracted to the pen tube. Same thing we can try with pieces of paper. Here also the pieces of paper get attracted. So that's again static charges. So here again I have a straw, a plastic straw, that also can be used to do the same activity. We can rub this with a piece of cotton cloth or with a piece of polythene sheet. So first we'll see whether it attracts regiform balls and paper. Now if we hold it near regiform balls or pieces of paper, it does not get attracted. But if I rub it with a polythene sheet, now if I hold it near regiform balls, you can see they get attracted. So that is again due to the static electric charges formed on the surface of straw. Now again pieces of paper, you can see they get attracted to the surface of the straw. So that is also due to the static electric charges formed on the surface of the straw. So these are all insulator materials. Then I have here an ebonite rod. Now this also can be used as the insulator material. If we just hold it near regiform balls or pieces of paper, there is no attraction. But when I rub it with a piece of woolen cloth or wool. Now here, if I rub it nicely, and you hold it near regiform, here you can see they get attracted. Same thing we can try with tiny pieces of paper. Here you can see the pieces of paper get attracted. Here you can see. So all these are due to the static electric charges formed on the surface of this insulator material. Comb, tube of a pen, straw, ebonite rod. And also I have a PVC pipe here. Now if I hold this also near pieces of regiform and pieces of paper, nothing happens. Now here you can see it does not attract any of these. But if we rub it with a sheet of polythene. So here if we rub it nicely with a sheet of polythene, and if I hold it, here you can see it attracts tiny pieces of regiform. So like that students, we can use different insulator materials. We rub them with different types of cloths or different materials like polythene sheet, wool and also cotton cloth. You all can understand that there are charges formed on the surface of the insulator and that attracts these tiny substances. They have to be very light. That's why we use tiny pieces of regiform, tiny pieces of paper. Even dust will get attracted to these surfaces. So that is static electricity. Charges that do not move and that are formed on the surface of insulator materials. You all have to understand that, students. Okay, students. So now I am going to do this activity in order to understand how electricity flows, that is electric current, can be generated from static electric charges. So as you all know, when we have an insulator material, if we rub it with another material, for example, a PVC pipe is an insulator material. When we rub it with a sheet of polythene, there are static electric charges formed on the surface of PVC. So if we connect those charges to a conductor, then of course the charges can flow through the conductor and that will become the electric current. So to do that activity, we need a neon bulb. So here I have a neon bulb and the two terminals of the neon bulb are connected to conducting wires, copper wires. So similar to that, here I have another neon bulb. I have attached it to the surface so that it won't move while I do the activity. And here I have connected the two terminals to copper wires. And on this side, I have a long wire that is connected to the earth there. So it's a long wire. Whereas on this side, I have the terminal with the open end. So this is what we are going to do. I'll be taking the PVC rod. I'll rub it with a polythene sheet. Then after rubbing it, I will touch the conducting wire on this end because this end is connected to the earth. So here, if I just touch it, now you can see nothing happened because there are no charges on the surface of PVC. So there are no charges flowing through the neon bulb. And you all have to remember, students, even a very small amount of charge, that is the static charges generated on the surface, is enough to flow through the neon bulb and to make it light. There are different types of neon bulbs, but this one, it can light with this small amount of charges. That is why we use the neon bulb. So now I'll be rubbing this with the sheet of polythene and then I'll be touching it here. And then I will have to touch it to the conducting wire. Here can you all see the light? It came on and immediately it went off. So that is how it happens. I rub the PVC rod with polythene sheet. There are charges generated on the surface of the PVC pipe, that is the static electric charge. When I touch it on this conducting wire, the static charges flow through the copper wire and through the neon bulb to the earth on the other side. So there, when the charges flow through the conductor and the bulb lights, it is the electric current. So that is when charges flow through a conductor. So can you all understand the two types of electricity? Static electricity on the surface of an insulator. But when that is in contact with the conductor, the electric charges flow through the conductor and the bulb lights. That is the electricity that flows. So current, electricity. And why does the bulb go off? Because there is a small amount of charge on the surface and that also flows through the conductor to the earth. So that is why until the charges flow, the light is on. When the charges are not there anymore, not flowing anymore, the bulb turns off. So that is how we can convert static electricity to current electricity. I'm sure you all can understand that, students. Okay, students. So this is a simple activity. We will do this to understand the direction of current flow and the direction of electron flow. As you all know, when we have a dry cell, I have a dry cell here, there is a positive terminal and the negative terminal. So when there are terminals, the negative terminals, there are more electrons, that is why the negative charge, negative terminal, and in the positive terminal, there are positive charges. So there is a charge difference, a pressure difference that will drive the flow of electrons through the conductor when the circuit is complete. So that is what we call as potential difference. And when there is a potential difference, there is an electromotive force that drives the electrons to flow through a conductor. And always, since there are more negative charges in the negative terminal of the dry cell, that is the power source, electrons will flow from the negative terminal through the conductor towards the positive terminal. But as a convention, we say current flows from the positive terminal through the conductor towards the negative terminal. So electrons flow from the negative terminal through the circuit towards the positive terminal, while the current flows from the positive terminal towards the negative terminal through the conductor. So for this to happen, for the electrons to flow and the current to flow, there should be a complete circuit. Now here I have the dry cell. The positive terminal is connected to this terminal of the bulb. This part is connected to the other terminal of the bulb, but here the circuit is not complete. So you don't see the bulb light because there is no current flowing through it. So now I'm going to connect this terminal to the negative terminal of the dry cell. Then you have to look at the, here you can see. Can you all see? The bulb lights. So now the circuit is complete. So from the negative terminal of the battery, the electrons flow through the circuit to the positive terminal. Whereas current conventionally flows from the positive terminal through the conductor towards the negative terminal of the battery. So that is how current electricity flows through a circuit. You need to have a complete circuit, and always electrons flow from negative terminal through the circuit towards the positive terminal of the battery, and the conventional current flows from the positive terminal through the conducting circuit towards the negative terminal of the battery. So that is a complete circuit, and there is electric current or current electricity flowing through it. Okay, students. Now I am going to do this activity to observe how an ammeter needs to be connected to a circuit in order to measure the current flowing through the circuit. So firstly, you all know there needs to be a power source. So here I have two dry cells. Now you all know dry cells have the terminals positive and negative. So when you connect the dry cells, positive terminal, negative terminal, then the positive terminal of the next dry cell and the negative terminal. Then to the positive terminal of the dry cell, I have connected the switch there. So you all know this is a switch you can use to on and off the current flow. So switch, and then it is connected with the bulb, and there from the bulb a wire is connected to the positive terminal of the ammeter. Now this is an ammeter. You can see the A indicated there. Now you all know current flow or current is measured in amperes. Amperes is the SI unit, capital A, and the instrument is ammeter. So that is indicated with that capital A there. Then the negative terminal of the ammeter is connected to the dry cell. Now in this circuit, you can see, students, the current flows through this red color wire to the terminal of the switch. From the other terminal of the switch, you can see there is a connection to the bulb. From there to the ammeter, again back to the dry cell. So it is flowing continuously. This type of connection is known as a series connection. Now all the current from the dry cell, all the current that flows through the bulb flows through the ammeter. Then only you can measure the current flowing through the bulb. That is how we are supposed to connect the ammeter. It is known as the series connection. Now when I switch on the switch or close the switch, you have to observe the light bulb and the ammeter reading. Now I am going to close the switch. Now it's on. Circuit is complete. So here you all can see, students, the bulb lights and also you can see the ammeter reading. Since I have connected to this terminal, you have to look at the bottom reading. So 0.2, 0.2, then it is 0.3 amperes. So the current flowing through the bulb and the ammeter, the same current, that is equal to 0.3 amperes. So that is how you read the ammeter, and that is how we determine or measure the current flowing through a circuit. All the current that flows through the bulb flows through the ammeter as well. That is very important. I am sure you all can understand how we are supposed to connect the ammeter to a circuit. So with that, I'll off the switch or open the switch. So there is no current flow. Then here you can see it comes to 0. So because there is no current flow, the bulb does not light, and also there is no ammeter reading, or it shows 0 reading. So that means there is no current flow. Okay, students. So now we will see how we need to connect a voltmeter to a circuit if you want to determine the potential difference. So as you all know, what is potential difference? Now if you take a dry cell, there is a positive terminal and a negative terminal. Near the positive terminal, there are more positive charges. Near the negative terminal, there are more negative charges or electrons. Because of that, there is a pressure difference generated when the dry cell is connected in a circuit. Now, due to this pressure difference, there is a force or a potential difference between the two ends of the battery. Because of that, electrons flow from negative terminal to the positive terminal, and we say conventionally the current flows from positive terminal to the negative terminal. So the pressure difference that causes the electrons to flow is known as the potential difference. And the standard unit of measuring potential difference is the volts. And because of that, we call it the voltage. Potential difference or volts, voltage. And the instrument used to measure the voltage is the voltmeter. So here you can see it's indicated with the letter capital V for volts. Now I have connected the circuit. You can see two dry cells are connected. As you all know, positive terminal, negative terminal. Positive terminal of the next battery with the negative terminal on this side. Then here you can see both the terminals are connected to the bulb. Now this is the negative terminal connected, and the positive terminal of the bulb is actually connected to the switch, and from the switch a connection is given to the bulb. So this side bulb is in contact with the positive terminal through the switch. This is the switch, and on this side the negative terminal is connected. Now look at the voltmeter. We need to measure the potential difference across the bulb only. So if you want to measure the potential difference across the bulb, the terminals of the voltmeter have to be connected here. Now here you can see this terminal is connected to the voltmeter, and this side also the terminal is connected to the voltmeter. Is that clear, students? So this is how you are supposed to connect. This is a parallel connection. Now this is parallel to the bulb and the dry cells. So mainly it has to be parallel to the bulb because we need to measure the potential difference across the bulb. So these 2 points, between these 2 points. That is why the voltmeter is connected in such a way. Now here you can see you're familiar with the switch. Switch is open now. Open means it's off. So there is no current flow through the circuit. Now when I on the switch or close the switch, you can see the bulb light and also you can see a reading in the voltmeter. It is 2.8 volts. So the potential difference across these 2 points, the 2 terminals of the bulb across those 2 points is 2.8 volts. So that is how we measure the potential difference. So when I turn the switch off or open the switch, the circuit is not complete. So the bulb does not light and you don't see any reading here. So there is no potential difference across the bulb. The main thing is that, students, you all have to remember voltmeter is connected parallelly to the bulb, parallelly to the points between which you want to measure the potential difference. And in this case, the 2 points on either side of the bulb. So the potential difference across the bulb was measured by the voltmeter connected parallel to the bulb. So you all know how to indicate this in a circuit diagram also. I am sure you all can understand this connection very clearly. Okay, students. So now I am going to do this activity in order to understand that there should be a potential difference across the terminals of the battery or the dry cells in order for a current to flow through the circuit. So to do this activity, we need 2 dry cells. So in a dry cell, you all know this brown color side, that's the positive terminal and this is the negative terminal. Here again, positive terminal and negative terminal. Then I have the ammeter here. You can see a ammeter to read the current flow through the circuit. Then we have the voltmeter here. You all can see the letter V. So voltmeter to measure the potential difference across the bulb. And you are familiar with how connecting the ammeter and the voltmeter to a circuit. So here you can see the ammeter is connected in a series manner with the bulb, so that all the current that is flowing through the bulb will flow through the ammeter. Whereas the voltmeter is connected to the 2 terminals on either side of the bulb, so that the potential difference across the bulb will be read or measured using the voltmeter. Then I have the terminal of the ammeter, here terminal of the bulb connected to the conducting wires. You can see the rest of the conducting wires there. Now I will be using these batteries and connecting them in different ways to understand that when there is no potential difference, there is no current flow, and when there is potential difference, there will be current flow. So first what I will do is I will have both the positive terminals connected together. So I am going to connect the negative terminal to the ammeter here, and then I'll have the negative terminal connected to the bulb. So I will be connecting the positive terminals. I will be connecting the positive terminals of the bulbs together. This is the positive terminal. I am going to connect with the other positive terminal. Now observe the circuit. Is there any change? The bulb does not light. You don't see any voltmeter reading. So no potential difference, 0 potential difference, and ammeter is also 0. So there is no current flow. When there is no potential difference, 0 potential difference, there is no current flow. Because we connected the 2 positive terminals, there is no charge difference, there is no pressure generated due to charge difference. Therefore, there is no potential difference. You can confirm that looking at the voltmeter. 0 potential. and therefore there is no current flow. So 0 reading in ammeter and the bulb does not light. So that is the first circuit. When you connect the two positive terminals, there is no current flow. Then I'll remove this. Now what I'm going to do is, I'm going to connect the positive terminal of the dry cell to the bulb. The same way, the positive terminal of the cell to the ammeter, and then the negative terminal of this battery to the negative terminal of the second battery. So here I will connect the negative terminal with the negative terminal of the other battery. Now here also you can see negative and negative terminals are connected. Can you see any change here? The bulb does not light. Voltmeter reading 0. Ammeter's reading 0. So that means there is no potential difference and there is no current flow through the circuit. Why is that? Because both the negative terminals are connected together. Both are electrons. They are high in negative charges. So because of that, there is no potential difference. There is no pressure difference due to charge difference. Because of that, there is no potential difference. Again, the reading 0, there is no current flow. So in these two instances, when you connect the identical terminals, negative and negative or positive and positive of dry cells, there will be no current flow. So what do? We need to connect the positive terminal of one battery to the negative terminal of the second battery. So now I have the positive terminal, negative terminal, positive terminal, negative terminal. So here I will connect it to this. Then if I connect the positive terminal of the second battery with the negative terminal of the first battery, you all can see the bulb light. So here you all can see a potential difference across the circuit, 2.8 volts. And here you can see an ammeter reading 0.3 amperes. So now it is confirmed. When you connect the terminals correctly, positive, negative, then positive, negative. So between the terminals, there is a potential difference. Because the charges are separated, there is a charge difference, and because of that there is a pressure difference. That is the potential difference. That is what we read here in the voltmeter, and because of that there is a current flow and you can see the bulb light as well. So always for the current to flow through the circuit, there should be a potential difference across the terminals of the battery or the dry cells. That is what you need to understand from this activity. Okay students. So now I am going to do this activity in order to observe whether there is a relationship between the current flowing through a conductor and the potential difference across the conductor. So to do this activity, now I have the batteries. There are 4 dry cells. So there is a potential difference and the dry cells are connected in the correct manner. Positive terminal, negative, positive, negative. Likewise, I have connected them properly. Then I have this ammeter here in order to measure the current flowing through the conductor. Then the switch is there to turn on and off the circuit. Then we have the voltmeter here to measure the potential difference. Now here I have this coil. You all know this is a nichrome coil. Now nichrome is a material that has very high resistance. So because of that, when current flows through nichrome, there will be heat generated. So you have to make sure throughout this activity that the amount of heat generated or the temperature of the nichrome coil does not change. Because if temperature changes, the resistance of the circuit will change. So in order to make sure that it does not happen, we have to make sure that the temperature does not change. And as I said, the voltmeter is connected to the 2 terminals of the nichrome coil. Here you can see this terminal is connected here, this terminal is connected here. So we will be measuring the potential difference across the nichrome coil, and the ammeter reading will be the current flow through the nichrome coil. Those are the materials. Then we have this instrument here. Now this is a rheostat. Now if you look at it, if I show it to you in this direction here, you can see it's written as rheostat, and this is a resistor, a variable resistor. We will be discussing resistors and this particular variable resistor later in the lesson. Now if you look at it, here you can see there is a coil, a wire coil made up of again nichrome. So this nichrome has very high resistance. So that is why we are using this as the variable resistor. Then here you can see there are 3 terminals. Now what I will be doing is, I'll be connecting one terminal to one end of the switch and then this terminal. So between these 2 ends is going to be the resistance. So that is how the rheostat is going to function. Now when I have the 2 terminals connected like this, here you can see this knob, this part is towards the extreme end. So there are these coils. Now here see, this rod is in contact with this particular knob. So all these coils are in contact with this part, and that is in contact with the rod. So that is connected to the knob here. So this whole thing will give the resistance. If I move it to this side, now from here to here is the nichrome coil, then that is in contact with the rod, and here that is in contact with the knob. So this part of the nichrome coil will give you the resistance. So now what I am doing is I am decreasing the resistance. If I push it further here, only this part, the resistance decreases. When I bring it to this point, no resistance or the minimum resistance is there. That is how we change the resistance using this variable resistor, that is a rheostat. So now I am going to connect it to the circuit here. I'm going to connect this terminal and this terminal. Now everything has been connected. The dry cells, ammeter, switch, rheostat, voltmeter and the nichrome coil. So every time when I turn on the switch, I will be changing the rheostat before I turn on the switch. So different values of resistance provided by the rheostat. At that time, you have to look at the readings of the voltmeter and the ammeter. So that is how we are going to do the activity. Turn on the switch, look at the readings, write down the readings. But before that, as we take the readings, we have to turn off the switch. The reason I told you all, this is a nichrome coil. It has very high resistance. Because of that, when current passes through it, there will be heat produced. This will become hot. To prevent the temperature of the nichrome coil from increasing, we have to close the switch, immediately take the readings and open the switch. Like that, we have to repeat the activity about 5 times and get the readings for ammeter and voltmeter. I'm sure you all can understand the activity. We will do that now. So now here you all can see, students, I have set the ammeter, voltmeter so that you can see the readings, and here I have pushed this knob to the extreme end. So the resistance is very high at this point. So now when I close the switch, the circuit will become complete. Have a look at the voltmeter and ammeter readings. So here I am going to close it. There is no deflection because the resistance is high. There is no current flowing through the circuit. So I'll open the switch. I'm going to set the rheostat to a certain value. Then I'm going to close the switch so that the current flows through the circuit and the coil. So you all have to get the ammeter and voltmeter readings. So when I close the switch, observe the ammeter and voltmeter. So here you all can see, students, the voltmeter reading 0.2 volts and ammeter reading 0.1 volt. So it was 0.2 and 0.1 ampere, 0.2 volts and 0.1 ampere. Now I'm going to change the variable resistor a little bit and then I will close the switch. Now if you look at the readings, we might have to change the resistance a little bit more. I'm changing the rheostat, the resistor. So here you all can see, students, 0.4 volts and 0.2 amperes. I'll switch it off and switch on again. And we have to make sure the coil is not hot. So I'm going to change the resistance. So now you all can see the voltmeter reading 0.6 volts and ammeter reading 0.3 amperes. Then still the coil is not hot, so I will change the resistor. Now look at the voltmeter and ammeter readings, 1 volt and 0.5 amperes. So I'll open the switch, 1 volt and 0.5 amperes. Then again I will change the resistor, the minimum value. So I have brought the rheostat to this end, almost towards this end. Now I will again on the switch. Now if you look at the readings, can you all see the readings? The voltmeter and ammeter, 3 volts and 1.5 amperes. So 3 volts and 1.5 amperes. I will switch it off. Now we have all the readings there. From these values, by just looking at the value itself, you can see, students, volt over ampere. So 0.2 divided by 0.2 divided by 0.1. You will get the value 2. Same way if we do 0.4 divided by 0.2, that also 2. Like that we will have to divide all these values. Then we will have to divide all the values, get the ratio between voltmeter reading, that is the potential difference, and the current flowing through the circuit. So from this, you can see when the potential difference increases, the current flow increases. That is the relationship. But when we divide potential difference by current, you can see we get a constant value. And that is what we will be calling as resistance, and from that we will be coming to the point where we discuss the Ohm's law. So I am sure, students, you all understood the activity, how we connected the circuit, why we need to maintain the temperature. The temperature of the nichrome coil should not increase. Then of course the current flow, the resistance will change. Because of that, the current flow will change. So to prevent that, we have to maintain the temperature constant. That's why we have to close the switch, immediately take the reading and open the switch so that it doesn't get hot. Like that, we got 5 sets of readings. So from that, you all can understand that there is a relationship between the potential difference across the circuit and the current flow across the circuit. Okay, students. So now I am going to do this activity in order to understand the factors that affect the resistance of a conductor. Or we will try to see how the different factors. There are 3 factors that we discussed. The cross-sectional area of the conducting segment. Then the length of the conductor, the length of the segment of the conductor, and also the material composition of the conductor. So to do this activity, we need the power supply. So I have the dry cells here, all connected in the proper manner. Then you can see the positive terminal of the dry cell is connected to the positive terminal of the ammeter, and the negative terminal of the ammeter is connected to a bulb. Then the other end is open here. I'll be connecting it with the conductor. The same way this side. the negative terminal of the batteries is connected to the switch. So now I have this open end which I can connect with these nails on this board, and on this side also I have this end that is connected to the bulb that can be connected with these different nails. So then these are the conductors. Now you can either have a metal rod and tie the wires, conducting wires, the metal wires to that on one side so that it will be fixed. Otherwise, we can have nails like this on either side so that we can connect the two crocodile clips and use the different conductors. So now here you can see the conducting wires are labeled. Now the number 1, 2, 3. All of these are made up of the same material, nichrome. And also here you can see they have the same length. So material is the same, length of the conductor is the same. Only difference is the area of the cross section or cross-sectional area of the conductor. Now this one, the first one is the most thickest wire, second one is a little bit more thinner, and the third one is very thin comparatively. So the first one has the highest cross-sectional area, the second one has the medium cross-sectional area, and the third one has the lowest cross-sectional area. Then if we take the conducting wires 3, 4 and 5, you can see they have the same length and they have the same cross-sectional area, but they are made up of different materials. 3 is nichrome, 4 is copper and 5 is iron. So different materials. Then you take the conductors 5, 6 and 7. They have the same thickness. They are made from the same material. Everything is iron. Only thing is the distance, the length is different. 5 is the longest one, 6 is shorter than that, and 7 is the shortest conductor. So now what I'll be doing is I will connect this end to this nail and this end to that nail for one conductor. Then we'll close the switch, and at that time look at the ammeter reading and the brightness of the bulb. That is what you need to observe. So here I'm going to connect this end here and this end here, and we will turn on the switch. When I turn on the switch, you can see somewhat bright. We have to compare and you have to look at the ammeter reading. The ammeter reading is 0.4. So I will note that down, 0.4. Just observe the brightness. I will turn it off. Then we will connect it with the second set of wires with lesser cross-sectional area. Now again, I am going to close the switch. When I close the switch, now you can see. So here, look at the ammeter reading. What is the reading? 0.3 amperes. 0.3 amperes. And if you can remember, the brightness is somewhat lesser than the previous brightness. A little bit less. So I will put 3 ticks for the first brightness, 2 ticks for the second brightness. Now I am going to turn the switch off. Then the third conductor, the lowest cross-sectional area. Now we will close the switch, complete the circuit. Now can you all see? The bulb it lights but very less brightness. And look at the ammeter reading. What is the ammeter reading? The ammeter reading is 0.2 amperes and very less brightness. So now you all can understand what happens there. The first 3 conductors are made up of the same material, same length, but what happens? The cross-sectional area is different. When the cross-sectional area is high, the highest cross-sectional area, the current flow was 0.4 amperes and the brightness was highest. When cross-sectional area decreased, current decreased and the brightness of the bulb decreased. So from that you can understand when the cross-sectional area is high, there is more current flowing through the conductor. That means the resistance of the conductor is less. So now we are trying to understand the factors that affect the resistance. Cross-sectional area more, resistance is less. Cross-sectional area is less, resistance is more. So that is how the cross-sectional area of the conductor affects the resistance. Now we will observe the next three conductors. Again, third one also we did, but just to compare, we will start from that. Now here you can remember we have a very light brightness, very less brightness and 0.2 amperes with nichrome conductor. Now I am going to connect it to the fourth one, that is the copper conductor. Now copper, when we close the switch with the fourth conductor. Now look at the brightness. Very bright, and look at the ammeter reading. So the ammeter reading is 0.4 and also very, very bright. So now I am going to switch this off and connect it to the fifth conducting wire, that is made up of iron, the same length but the same cross-sectional area. So 3, 4, 5, same length, same cross-sectional area. Only thing that is different is the material. So I have written down the value. Again I am going to on the switch. Now here you can see the brightness is somewhat less, and look at the ammeter reading, 0.3 amperes. So 0.3 amperes and less brightness. Now if you look at the three conductors, 3, 4 and 5, nichrome, copper and iron. You can see the area, cross-sectional area is the same, length is the same. Only thing that is different is the material. Through copper, the brightness was the highest and 0.4 amperes. Highest current flows through copper. That means the resistance of copper is the lowest compared to the three. So after copper, if you look at it, it is iron, 0.3 amperes. So that has a little more resistance, and nichrome has the highest resistance by 0.2 amperes, and the brightness was the least. So now you all can understand this factor, that is the nature of material or the material composition of the conductor, is actually known as resistivity of the conductor. So that is the second factor that affects the resistance. That directly depends on the material or the resistivity of the material. Then we have the wires 5, 6 and 7. All of them are made up of the same material, iron. They have the same cross-sectional area, but they have different length. Again, just to compare, I have already connected it to the fifth conductor, that is the iron wire, iron string. Now you can see the brightness and the ammeter reading 0.3 amperes. I will switch it off, connect it to the next wire, sixth one. Can see here. Then if I close the switch, now the length has decreased. So here the brightness is more. Look at the ammeter reading 0.4. So 0.4 and the brightness is also more. So I'll switch it off and then we will connect it to the shortest conductor made up of iron. So now look at the brightness. It's very much brighter, and look at the ammeter reading 0.5 amperes. So here I will turn the switch off, 0.5 amperes and very high brightness. So there, if you compare the three conductors 5, 6 and 7, same cross-sectional area, same material iron, but the length is different. When the length became shorter, the shorter wire, the brightness was more, current was more. That means when the wire is short, the resistance is less. The longest wire, less current, 0.3 amperes, and the brightness was less. That means the resistance of the longest wire was the highest. So from that you all can understand. When the length of the conductor increases, the resistance increases. So we wanted to observe the factors that affect the resistance of the conductor. When the cross-sectional area increases, the resistance decreases. Then material composition determines the resistance. That is what is related to resistivity of the conductor. And then when the length decreases, the resistance also decreases. Those are the three factors and the way they affect the resistance. I am sure you all can understand that clearly. Okay, students. So now I am going to do this activity in order to understand the action of resistors. So when we say resistors are used to control the current flow through a circuit. Like how we use a tap to control the water flow, we use a resistor to control the current flow. And there are different types of resistors. In this activity, we will be using 3 resistors which have fixed values. So I will be using a 5 ohm resistor. This is actually mounted, the resistor. If you open this and look inside, so here you can see this is actually the resistor. They have different color codes. We will be discussing that later. But here this is a resistor. For convenience, it is mounted in this manner so that you can easily connect the crocodile clips to these 2 terminals. Here you can see this is a 5 ohm resistor. Then we have a 10 ohm resistor and a 20 ohm resistor. So I will use the 5 ohm resistor first. If you look at it, I have connected 4 dry cells, 4 batteries. So they are connected in the correct manner, positive, negative terminals alternately. So the potential difference is there. Then the switch is connected there, and thereafter you can see the bulb that is also connected. So between these 2 terminals, I will be connecting the resistor. First, I will start with the 5 ohm resistor. When I connect it, have a look at the brightness of the bulb, or look at the bulb. So here I am going to connect the resistor, the 5 ohm resistor. So now the 5 ohm resistor is connected. If I turn on the switch, then only the circuit will be complete. So when I turn on the switch, now look at the brightness of the bulb. It is somewhat bright, so you can say the bulb lights and the brightness is there. Now we will have to compare the brightness of the bulb with different resistors. So I'll turn the switch off. Then I'll have to remove the resistors. Then I'll use a 10 ohm resistor. Then again I'll close the switch. Now you can have a look at the brightness of the bulb. This is less brighter than the previous one. Why is that? The resistance increased, the brightness decreased. So from that you can understand when the resistance increases, the current flow decreases. Because the current flow decreases only, the brightness of the bulb decreases. Now we will try with the third resistor also. I'll turn it off and change the resistor. Now the 20 ohm resistor. With that, if I close the circuit, now can you all see the bulb? It lights but very less brightness. So now the resistance has increased. 20 ohm resistor, the brightness of the bulb is very, very less. So that is the activity. Now from these observations, initially I had the 5 ohm resistor, the bulb was very bright. Then with the 10 ohm resistor, the brightness decreased a little bit, and now with the 20 ohm resistor, the brightness is very less. So from that, you all can understand, students. Normally when there is more current, brightness will be more. Less current, the brightness of the bulb will be less. So when we have a less resistor or low resistance in the circuit, there will be more current flow, so the bulb will be very bright. But when we increase the resistance using a different resistor, the current flow decreases. Because of that, the brightness of the bulb decreases. So you can understand When resistance increases, current decreases. So that is how we use the resistor. By using a higher resistor, we reduce the current flow. Using a lower resistor, we increase the current flow. That is how we control the current flow through a circuit using resistors. I am sure you all can understand that easily. Okay, students. So now we will look at different types of resistors. You all know what a resistor is. Resistor is used to control the current flowing through a circuit. And to do that, we have different types of resistors. And this is the first type that we discussed, fixed value resistors. When we say fixed value resistors, the resistance of that particular resistor does not change. So if you fix it to a circuit, that is a fixed resistance and that will not change. Because of that, only a certain amount of current will flow through that particular circuit. We cannot change the value of the resistance during the activity. So some examples or some of the fixed value resistors are here. I will show them to you. Here you can see, students, if we look at this cylinder-like structure is a fixed value resistor with the two terminals. So with these two terminals, we will be attaching the resistor to the circuit. And here, can you all see, in this there are color bands. Color bands of different colors. We'll be discussing how to calculate the resistance value of a resistor using this color band. And in this, if you all look closely, there are four color bands. The first three color bands are somewhat close to each other, and on this side you can see the fourth color band. So always when you look at a resistor, you have to hold it in such a way that you read the first three color bands. The color bands that are close to each other are towards your left side. So they are the first three bands. And the fourth color band is the band that is away from the other three bands. That will be on the right hand side to us. So for me, this is how I'll be reading the resistor. So for y'all, you will have to look at it like this. Starting from this band, the three bands, then the fourth band a little away from the rest. So this is a fixed value resistor. Now there is a difference between this and this one. The colors, the size, the color bands, everything is different. That means the resistance of this resistor and the resistance of this resistor are different values. They are fixed values but of different resistance. Like that, I have another resistor here. So this is different from this one. So they are all fixed value resistors. Then we have this one. Now this is a fixed value resistor that is easy to use in a circuit. When connecting, here you can see the two terminals. You can connect the conducting wires to the two terminals using the crocodile clips. It's easy to connect, and here the resistance is denoted as 10 ohms. Now if I open this, you all can see here the 10 ohm resistor. This is a 10 ohm resistor. So you can look at the color bands also there. So this is a fixed value resistor connected in such a way or mounted in such a way that we can use it easily in a circuit. So that is also a fixed value resistor, 10 ohm resistor, and these are different fixed value resistors. So I am sure you all can identify different fixed value resistors easily. Okay, students. So now we will look at some examples of variable resistors. So as you already know, variable resistors are connected to the circuit and we can adjust the value of resistance. Either we can adjust the value and then connect it to the circuit. If you want to change the value again, you have to remove the resistor, change the value and connect it back. Or while doing the activity, while the resistor is connected to the circuit, we can adjust the value of resistance. Both types come under variable resistors. As examples, we can look at three types of resistors. I have two of them here. The first one, rheostat. We have already used this in a circuit, in an activity, so you're familiar with this. The rheostat is a variable resistor. Now in the rheostat, you all can see students, this is the nichrome wire coil. And nichrome is a material that has very high resistance. Now there are 3 terminals shown here. If we connect this terminal and this terminal, then when this knob is on this side, it is touching only a very few coils. So that means the resistance is less. But if I move this part somewhere here, now you can see these coils come as the resistor. So the number of coils increases. So we connect the 2 terminals here and here. So the connection is with this, and this metal rod is connected to this knob here. So this part is the resistor. So when the number of coils increases, the resistance increases. We can further bring it to this side. Again, you can see the number of coils increases further, resistance will increase further. If we bring it to this maximum position, the full resistor is in effect. The full length of the resistor is in effect. Full length of the rheostat. So that will give maximum resistance. So here you all have to remember, students, by increasing the resistance, we will be decreasing the current flow through the circuit. Now the same way, if you want to use these 2 terminals, then what will happen is, if we move this knob here and connect these 2 parts, the resistance will be from this part of the coil. So when you keep on moving it to this side, the length of the nichrome coil will increase, so the resistance will increase. That is if you use these 2 terminals. Normally, we go for these 2 terminals, but if it is needed in a particular circuit, you can use these 2 terminals as well. What if you connect these 2 terminals? Then, of course, you will have the maximum resistance. Why? All the coils are coming between these 2 terminals. So then also it will be the maximum resistance. If we want to adjust the resistance, we have to use these 2 terminals or these 2 terminals and adjust this knob so that the resistance changes. So that is how a rheostat functions. It is an example of a variable resistor. Then we have the next one, a volume control knob. Now here you can see, if you look closely from this side, you can see there are pins. Those are connected to the circuit board, and this part is there, and this is the knob that we can rotate. Now here I can rotate this knob. So that is like a volume control knob. So by rotating the knob, you can change the resistance. So this is a volume control resistor or volume controller switch or volume controller that can be rotated, and thereby the resistance can be varied. So that is also an example of a variable resistor. Then you are familiar with pre-adjustment resistors. So like I said, these 2 resistors, you can change the resistance while they are connected to the circuit. But pre-adjustment resistors, you have to set the value of the resistor and fix it to the circuit. If you want to change the value, you have to remove the resistor, change the value again, and then connect it to the circuit. So all these 3 are variable resistors. So we have been discussing about different types of resistors, and under that the 3rd type, that is the light dependent resistor or the LDR. So here I have 2 LDR. If you look at the LDR here, can you see the surface? So that part is sensitive to light. When light does not fall on that surface, say if now there is light falling, if I cover it with my finger or if you cover it with a cloth, then there will be no light falling on the surface, or in the night time when there is no light, then the resistance of LDR will be very, very high. If that is connected to the circuit and no light is falling, the resistance will be high. There will be very less amount of current flow or no current flow at all. But when light falls on this surface of the LDR, the resistance decreases. And when resistance decreases, there will be current flowing through the circuit. So this is used in instances where we need to change the resistance depending on the intensity of light. And that is why it is a light sensitive resistor or light dependent resistor, LDR. So you have seen an LDR, I'm sure you will understand the function. This is also another LDR. And like I showed you all before, even the LDR has two terminals. Using these two terminals, we will be connecting the LDR to the circuit.